So basically regarding the format, Josh told me it's supposed to be like half an hour presentation, half an hour questions, but like not in that order. So feel free to ask questions at any point in time. Yeah, and Josh already introduced what I'm going to be talking about today. Basically, it's smart data analytics, and I'm going to present it with some biomanufacturing case studies that I've been working on in connection to a project that Josh and me are actually both working on together. Yeah, and I'm a PhD student in Professor Pratz's group. So with that, this is kind of an overview of the presentation. First of all, I'm going to talk a little bit about smart data analytics, like why are we looking into that? How can it be helpful? How can it be applied? And then the first topic is smart data analytics for predictive modeling. So this is basically all types of regression algorithms when I want to predict some form of continuous output. And the question is, what algorithm do I use in that situation based on the data that I have? I'm going to present it with a case study. The algorithm itself has been developed by somebody in our group that worked on it before I was there. So the algorithm itself is nothing that I've been working on, but the case study is something where I have applied the algorithm. So I thought I'll just do that first to give you an idea of what exactly smart data analytics is. And then the second part of the talk, I'm going to get into the smart data analytics for supervised classification, which is an algorithm that I've been working on, and I'm also going to present it with a case study. All right, so yeah, a little bit about motivation. Why is it actually interesting to look into that? In general, we have the situation that we have more and more data every year. This is kind of shown in this graph with the number of connected devices. In that case, connected devices to the internet. So all of those devices just more or less upload data that we can use or that we cannot use. It's up to us. So we basically end up collecting a lot of data, and we oftentimes do not really know how do we actually utilize that data in the best way. And that happens in a lot of different areas, but what I want to focus on today are manufacturing processes. So I'm in chemical engineering, so it could be chemical manufacturing processes, or like, as I will present today, biomanufacturing processes. And here we have a similar situation. We have our process typically up and running, and we collect data from a lot of data from that. So for example, pH values, temperature measurements, or like concentrations at different steps in the process. And this is by now common practice to just have all those measurements, and there are sometimes models that help you utilize those measurements, but oftentimes you just collect them and you don't really know how exactly am I going to use them. And also sometimes you're not sure which measurements you actually want to collect. So we have that situation that you have a lot of measurements and you use some of them, but probably not all of them, and you're not sure how to use them in the best way. And that is kind of the idea that motivates this whole smart data analytics approach. So in general, data analytics can work on different kind of scenarios. So we do have on the left-hand side the process modeling scenario where I just have a lot of data points, as I've mentioned before. In this case, it's just one dimension to make it easier. So we have my data points, and the idea is I want to predict some kind of output variable. And that could be whatever, maybe like a concentration of my final product. So I want to know whether it's in spec, out of spec, something like that. But yeah, in that case, I just want to find a model. In this case, it's just like a fairly simple linear model. In the real world, it's more complex. I have more input variables, but it's just one example. Another thing I could be looking into is process optimization. So similar to before, I want to first find my model, and then based on that model, I want to perform some sort of optimization. So let's say this is, for example, representing my cost function. How should I operate my different units in the best way to reduce the cost? And then on the right-hand side, we have the quality assessment part. So in that case, this is more of a classification problem. The first two were in the area of regression. In that case, I have my inputs, and I basically say, well, everything is fine with the quality. Threshold is just arbitrarily chosen to be 3. And if I'm under that threshold, I'm in normal operating conditions. That is good. That's where I want to be. And if it's over that, then I might want to take some action. Yeah, I just already got a bad internet connection, so please let me know if I cut out or anything. Yeah, so those are different ways to use data analytics, and smart data analytics is basically if I have one of those objectives, be it regression or classification, what algorithm should I apply? And I don't want to just try a lot of different algorithms and then choose the one that works best. I actually want to analyze the data and have an automated process of choosing the best model for whatever I want to do. Yeah, this was kind of the introduction or motivation of smart data analytics. So if you have any questions, I think we're a small group, so just feel free to speak and ask the question or also put it in the chat. Yeah, with that, that was a little bit of the motivation, and now I'm going to get into the model developed by a former student in our research group, smart process and modeling. I've already shown it before with the optimization example. But generally, I have my data points. Those
Fabian, you may want to turn off your video, and that might save some bandwidth on your side.
Okay,
if you have broken up a few times.
Okay, all right. Okay, I hope this works better now. So yeah, I have my data points, and I want to assign some kind of model for it that describes my process in the best suitable way. So once I'm there, okay. So this is the overview of how the smart data analytics algorithm works in the case of predictive modeling. So you can see this triangle with its 3 different corners, and then it has like those multicollinearity, nonlinearity, and dynamics. Those are characteristics you can find or not find in the data. So what you would do with this approach is that you would first analyze the data that you have that you want to perform your regression on, and you would analyze them for those 3 characteristics: multicollinearity, nonlinearity, and dynamics. I'm going to get later into how exactly you would analyze that. But once you found out which of those characteristics are present, you would then choose the suitable algorithm from this triangle. So if only one of the characteristics is present, you would go to the corners. So in the case, let's say that multicollinearity is present, I would go into this lower left corner where I have rich regression, elastic net, partial least squares. So those are generally algorithms that can deal with linear dependencies, and they also assign typically weights to some of the features that I use or some of the inputs. So I can give them a lower value, or I can even cut some of them out. For example, partial least squares is a dimensionality reduction technique. And that is pretty important, especially in manufacturing contexts, because oftentimes you measure a lot of different variables and you don't even have that many measurements. So the number of features or inputs is higher than the number of measurements. And in that case, multicollinearity is very likely, because you only have so many governing equations in your system. And that means that if you change one of the variables, the other variables depend on that. So in that case, if you detect multicollinearity, those are well-suitable algorithms in that case. Similar things can be said about the other corners, so nonlinearity. So there are some algorithms like support vector regression or random forest that might be familiar. ALVIN itself has been developed in our group. It stands for algebraic learning via elastic net. What is happening there is that it's a bit of a nonlinear extension of elastic net. So first you would create nonlinear features based on your given inputs that you have. Then you would perform some kind of feature selection algorithm, and in the end you would apply elastic net on whatever features you have chosen. So it kind of combines those different approaches with each other, which is also why you can see it on the edge from nonlinearity and multicollinearity. So the edges generally show approaches that work for situations or data where 2 of the characteristics are present. So in that case, ALVIN is on the nonlinearity and multicollinearity edge. Similar, you have other algorithms. For example, you have the whole dynamics side. Some of those consider dynamics by considering past inputs, for example, as for example CVA does. And we have RNN, which are recurrent neural networks. Those also consider past inputs by having a memory term in themselves. So there are generally different approaches to consider information from the past and therefore consider the dynamics in the system. I'm not going to get into detail into all those acronyms and algorithms, but this is just like a little bit of an overview, and the idea is to look at those characteristics, and based on that, you end up in the right corner or edge or the center of the triangle, and you have your subset of algorithms that are very important to look into. What is happening in the next step in this overall approach is that, let's say I figure out its nonlinearity. In that case, I have Alvin, support vector regression, and random forest, so nonlinearity in my data set. If I have those three algorithms, I would then perform a cross-validation between those three algorithms to figure out which one of those performs actually best on the data that I have. And then once I have done that, this already performs some kind of hyperparameter estimation. But once I have decided on like the best algorithm, I would still try to optimize those hyperparameters within the algorithm. So all that is currently published as like one program in Python. So if you wanted to, you could just download it, input your data, and it would do exactly that. It would tell you, I've analyzed the data, I found that there's nonlinearity, for example, no multicollinearity, no dynamics. As a result, I've analyzed the three algorithms, Alvin, support vector regression, random forest. And based on cross-validation, I found that, for example, support vector regression performs best, and here are the results. So it's already implemented and it works pretty well. And if people are interested in that, I can also provide the link to the paper and the software later on. That was the general idea for smart data analytics, and that applied to predictive modeling. Are there any questions at this point?
Yeah, Fabian, I have a quick question. It seems like the real key here is this identification of which part of the triangle you're in. And are you going to talk a little bit more about that? Yeah,
I'm going to get into how you determine those characteristics in the next slides.
Okay, sounds good.
Does the size of the data come into play at all here, or is that sort of lumped into the multicollinearity? So I could see some of these possibly working better for larger data sets and some working better for small data sets.
Yeah, so
that sort of get lumped.
I think I already touched upon that a little bit. So if you have a situation that you have a lot of inputs, a lot of features, and not as many measurements, you will have multicollinearity in your data because they all somewhat depend on each other. So you will detect this multicollinearity in every case, and you will already be drawn to it. It's possible that you have other characteristics also in your data, then you try to combine that with like those approaches on the edges or in the center, but you would always measure this if you have this type of data structure. In general, if you have a lot of data, it would just take the algorithm longer to predict something, which makes sense because it just, analyzing the data takes longer, applying the algorithm takes longer, but it can handle larger and smaller data sizes within some reason.
Thanks.
I have a follow-up question, and apologies if you are going to cover that later, but do you classify your data into one point of this triangle and then do your analysis using different algorithm, or do you do a combination of that?
So that is part of the algorithm. First, the data will be analyzed, and then based on that, you either end up in a corner, an edge, or the center of the triangle, and you already have your pre-selected algorithms, basically.
Cool, thank you.
Okay. All right, if there are no more questions, I would continue with the determination, with the calculation of the characteristics. So the characteristic multicollinearity is fairly straightforward. Multicollinearity just means that if I change one of my inputs, other inputs change with this single input. So what is actually happening is that I calculate the so-called variation inflation factor for each of the inputs. And that is, I'm trying to regress one of my inputs based on all the other inputs. And then I just calculate the R² value of that regression. So if I have collinear dependence, this R squared value will be fairly high, because if I see that I can describe input number 1 with inputs number 2, 3, and 4 almost perfectly in a linear fashion, those are, there exists multicollinearity between those. And in general, the threshold is that if this value is bigger than 10. So I've actually not applied this firsthand myself, but that is implemented in the algorithm like that. And I think it makes sense because like this is exactly how multicollinearity is defined. And so yeah, that's a pretty straightforward measure. What is a bit more complicated is the non-linearity characteristic. What is basically happening here is that different types of nonlinearity and linearity are analyzed. So the simplest approach is to do just like a linear correlation analysis, which would just be the correlation of my inputs with my output. And then I do that for each of the inputs, and then I basically get a value and take the absolute value of that. If it's 0, there's no correlation. If it's closer to 1, there's more correlation. That's typically how it works. And I think most of us are familiar with that. And then for the other tests, so those are basically tests for different types of nonlinearity. We do have the quadratic test and the bilinear correlation analysis, which are both formulated as hypothesis tests. So for the quadratic test, I basically say that my null hypothesis is that I do have a linear relationship, and my alternative hypothesis is that I do have a quadratic relationship. And in the end, I just apply both of those to my data set and then see whether the sum of squared errors for my null hypothesis or for my one hypothesis is bigger. I look at the difference of those, and there's a whole test statistic behind that. And ultimately, what's happening is that I'm also getting a value that is scaled between 0 and 1, where 1 means that I have quadratic dependencies and 0 means that there are no quadratic dependencies, and I will get something in between. So the higher the value, the more quadratic dependencies are in my data. That's also how the bilinear correlation analysis works, just that my alternative hypothesis is slightly different because I just have the combination terms of my different inputs. And then there is the last option, because this only covers a small amount of nonlinearities, but those are fairly common in manufacturing processes, which is why those are analyzed more in detail. And then the last one is the maximum correlation analysis, which basically analyzes a bunch of different nonlinear dependencies. So it just analyzes a total range of like functions or like nonlinear transformations you can form from your features, and also puts that in a value between 0 and 1. So in the end, what is happening is that you can basically look for all your variables, whether the linear correlation analysis, whether this value is higher, or whether any of those nonlinear analyses have a higher value. And if that is the case, if any of those nonlinear analyses yield a higher value than the linear correlation analysis, you would say that there is significant nonlinearity in my data, and you would go into the nonlinearity corner of this triangle, or in one of the nonlinearity edges, for example. And then we still have the last characteristic, the dynamics. This is also a fairly commonly used method. It's called the autocorrelation, where you basically correlate a time series with the time series itself, but with a certain time lag. So what you would expect for something that is just like a random distribution, for example, that there are no time dependencies, you would expect that this autocorrelation is like fairly low on the right-hand side, that they're all under this blue threshold line. I've created this autocorrelation plot by saying something like, my next value in the time series is twice the prior value. So in that case, you have clear dynamic dependencies, and you can see that in the result of this autocorrelation, because the second value still has a value that is higher than 0.8 and significantly over the blue threshold. So in that case, you can see that it actually detects those dynamic dependencies in the data. Yeah, so those were the three characteristics. So do you guys have any questions about that? You've already been interested in that before.
So
Yeah, I don't have any additional. Oh, go ahead, Chris.
I was going to say this third test, it's basically just seeing how autocorrelated the inputs are. Is that correct?
Okay, can you say that again?
It's basically just seeing how correlated or autocorrelated the inputs are. So
yeah,
how similar they are in time.
Yeah. And there are different approaches. So you can either perform this on the inputs, which is what you said. I think in that case, it is actually implemented on the outputs. So what is happening is that first the nonlinearities and the multicollinearities are assessed. Based on that, I would apply one of the algorithms in the triangle, and then kind of in a second pass over it, I would look at my outputs, see whether the outputs are still having this dynamic dependency on their on the output, but with a time lag, which is where I would use this autocorrelation function. And then if I find that this dynamic is still present in the outputs, I would consider using the dynamic methods as well. But yeah, generally you could apply it to inputs or outputs. And in that case, it's just implemented on the outputs.
Could it be the case that the output doesn't depend on previous inputs, but the inputs and the outputs are autocorrelated and sort of slowly changing in time, if that makes sense?
Well, the autocorrelation is just like either the input with itself or the output with itself. So I'm not sure what you mean, whether the output can be autocorrelated to the input.
So I was thinking that if the underlying system doesn't have the output be a function of past inputs or past outputs, you could still sort of detect dynamics if the inputs and the outputs are slowly changing over time, even if it's not a function of older inputs and outputs.
Yeah, okay. I think I know what you mean, but please correct me if I get it wrong. So typically in manufacturing processes, you always have some variables that do have dynamic effects. So if you just look at the inputs, you would always detect this kind of autocorrelation function as I've shown it here. However, that does not mean that the output necessarily has to have that. So there are situations in which like most of the inputs actually do have that dynamic behavior, but for the output, that is not the case. This can probably happen if the output is a function of like mainly the inputs that do not have those dynamic effects. So for example, if you use something like an elastic net or a ridge regression, and then the bigger weights are assigned to the ones that do not have dynamic effects, this can happen. But yeah, does that answer your question?
Sort of. I think it does.
Chris, I think you might be talking about a situation where you have you basically have stationary residuals, but you have a dynamic output. Is that what you're talking about? Like you have if you do the output minus your predicted value, that value is stationary over time, but you could still have dynamics in your output and your input at the same time.
I guess what I'm sort of asking is does this test just see if there's correlation in the outputs and in the inputs, or if the output is also a function of previous inputs, is what I'm asking.
So this test only analyzes the output in this algorithm.
Okay, I think that answers my question.
Okay.
It does sort of leave room for a potential, like for a potential other approach, right? So what I was talking about with the residuals, like if you were to estimate your model, like you said before, and this is the second pass. So if you were to look at the difference between your output and your predicted value, with your predicted value using a model that doesn't assume any sort of dynamics, and if those residuals have statistically significant autocorrelation, maybe that would capture not only it would capture a trend in the relationship between X and Y, which is really what you're interested in, right?
Yes, I think I know what you mean, but I can't imagine that happening, that like my residuals are stationary, but then I do still have dynamic dependencies in my output variable. So that would still mean that I do have dynamics that I need to consider, and then I would apply that, right? So
well, so if your residuals are stationary, then you know, regardless of the trend in your output and your input, the two would be trending in with the same, you know, with a stationary relationship, right? So I guess what are you, maybe we should go back to the triangle and see what you're trying to capture with the dynamics, like which models are chosen with dynamics.
Dynamic models actually do have that function that they oftentimes consider. They consider the inputs, they consider time lags of the inputs, and they also consider time lags of the outputs. So if I detect those dynamics, I would apply those algorithms that can handle those things. Maybe that answers your concern.
Yeah, I guess my point would be that the time when you would want to use those algorithms would be if you have a changing relationship between X and Y, not just that you have a trend in X or Y over time. And so it seems to me like looking for autocorrelation in the residuals would be that's probably would be my first thought in how you would detect a change in the relationship between X and Y over time.
Yeah, I don't like the residuals for the reason that I mentioned before, because you can have stationary residuals and you can still have an output variable that depends on itself, or that it has an autocorrelation with itself. So we thought about that a lot, because in what I'm going to introduce later is the classification problem. And there you cannot do it on your output, because your output is not a continuous variable. So autocorrelation itself is only defined for continuous variables. So, that was a problem I was facing back then. And I'm currently analyzing the inputs. And generally, I do find that the outputs are superior because of what I've mentioned before, that you can have a lot of inputs that do have dynamic effects, but still a dynamic algorithm is not the best choice because the actually important inputs do not have the dynamic effects. So that is something I'm still working on in that context. But that is also why I think that if you have the chance to look at the outputs, this is actually a very smart way to go about it.
Okay, thanks.
Have you looked at any physics-based models and or related these to the underlying physics, since you primarily are working kind of in the chemical industry? It would seem like there's flow models that you know, might be applied here. Do those relate directly to any of these corners, or have you looked at all at underlying physics for these rather than just correlations?
So do you mean mechanistic models of your process?
Well, you're trying to look for correlations between variables, and if you looked at the underlying physical equations of, you know, fluid flow or you know, any kind of pressure change, those have underlying models that are known, and I just wasn't sure if you're trying to apply any of those here.
Yeah. So that typically is not considered in this framework. That is something we would typically consider in the feature engineering part. So this is part of what you actually give to this algorithm. So if I know certain dependencies in my system, I can actually implement them directly. Like I only measure the variables x1 and x2, but I actually know that the output should roughly depend as a square function or as a cubic function on x1.
Right.
I can implement that directly.
Okay.
Yeah, and this is only a data-driven approach. So this is also the goal of it. So the idea is just, if you have your data, you can run this and it should give you the best suitable algorithm. But all that stuff is very important, like looking into your physical system. But you can use that by giving it the right features. So if you give better suitable features, the algorithms will perform better overall. So that is not something you can neglect if you use those approaches. This basically just automates the idea of a data scientist in that whole picture. Okay, so any more questions or can we continue? All right, I'm just going to go ahead with a case study. Yeah, so this is data that Josh is probably familiar with from our project. It's basically have a fat batch biomanufacturing process. I don't want to go too much into detail, and I don't know too much about the details either. So what is happening is that I have Raman spectra measurements, which look like the graph on the right-hand side. So I do have a certain wavelength, and for that wavelength, I have a given intensity. Those are all the measurements I have. So I do have that at like 900, 901, 902, 903. So I do generally have the situation that I have a lot of different features. For each of those wavelengths, I get an intensity, and each of those wavelengths is basically one of my features. So I think in that case, we do have, I don't know, something like 80 measurements and more than 3,000 features because we're going over a fairly wide range of Raman spectra. And the idea is that we can use this Raman spectra to actually predict the concentration of certain components in the fat batch process. And on the right-hand side, you can see that there's a graph for the glucose concentration. Those millimoles are different concentrations of glucose. And what you see is that those peaks at certain characteristic wavelengths get bigger the higher that concentration is. So in theory, you can conclude that based on this peak, the intensity of this peak, you can conclude how much concentration of glucose is in there. And there are several different peaks that are generally analyzed for the glucose concentration. They are shown here with those dashed lines. And you can either look directly at the Raman spectra, and then if you know those peaks, you can go in there, and there are relationships that you can roughly get the concentration of glucose. That is known for some of the components, for example, for glucose and for ammonia. But for others that we analyzed, it is not. But I'm just gonna present the glucose prediction because you can basically see the direct relationship in this graph here. And just thinking about it at this point, you would expect that you're going to end up somewhere in the multicollinearity corner, because we do have a lot of those inputs, and I can imagine that the wavelengths at 1,000, that the intensity at the wavelength 1,125 is somewhat related to the intensity at the wavelength 1,124. Because they are very, very close to each other. And the higher this peak is, the higher the points around it are as well. So this makes sense just from a logical point of view. And well, that's basically what I did. So we just took those Raman spectra. We just took out the baseline of the spectra so we can better analyze the peaks. And then based on that, we applied this algorithm that I've presented before. And this is exactly what is happening. So we're going to end up in this multicollinearity corner. And this is because the spectral data have a lot of features and we didn't have that many experimental values. And once I have that multicollinearity corner, a cross-validation between ridge regression, elastic net, partial least squares, and sparse partial least squares is applied. And what I find in the end is that partial least squares is the algorithm that performs best in that case. And you can see the prediction here. So overall, it's a fairly reasonable prediction. We have like two outliers, one here and one here. So that is something we're going to look into soon. So that's actually something I've presented like 2 weeks ago in our group. So it's a very recent case study. And then if you have applied this kind of algorithm, you can actually go the next step. So what we're currently looking into is which features have actually been selected. Does that fit with the glucose peaks that we would expect for glucose, to kind of physically validate the results and see whether this makes sense. And similar, we have done the prediction not only for glucose but generally for the biomass, the ammonia, and other components, and it works better or worse depending on the situation. This is probably like a medium result. So we have two outliers, which is not great, but overall the prediction is all right. And we had others where, especially where we had a lot of bundled values in a certain area, then the ones where we didn't have enough information didn't perform that well. So yeah, this is something that can be expected. And it kind of shows that this algorithm gives you the best suitable algorithm, but the results you get depend very much on the data you provide to the algorithm and also how much physical knowledge you put into it. Any questions regarding this?
Yeah, quick question for you, Fabian. Is there? It seems like there is an assumption that that there's no interpretability constraint basically within the framework. Is that correct, or is there a way to like constrain the set of algorithms that are chosen based on interpretable or not?
So if you use the algorithm, it actually asks you a lot of questions. Like it asks you, do you assume that there's nonlinearity in your data? So if you know that, you can already say, oh, I know there's nonlinearity, you don't need to analyze it anymore, analyze the other two. And one of those questions is also, do you want your models to be interpretable? So if you say you want it to be interpretable, some of the less or like harder to interpret models are not considered.
Okay, and what's your definition of interpretable?
I honestly don't know in detail how it was implemented, but I would assume that something like elastic net is like very easily interpretable.
Sure.
Something like random forest, you know, a regression tree itself is fairly easy interpretable, but if you have a lot of them, that gets a bit more difficult, or like recurrent neural networks can be very hard to interpret. So I would assume that, for example, those are not considered in that case.
Okay, thanks.
Okay, all right, and let's continue. Yeah, so now we get into the supervised classification. So this is more a work in progress. I currently have a manuscript for the algorithm, but it's not submitted yet. So yeah, I think you guys have an idea of what the idea of smart process data analytics is. And this is, I'd be happy about like any kind of recommendations or ideas. So please feel free to share your thoughts or ask any questions. Generally, first, I want to talk about what exactly is a supervised classification problem. So this is different from the prior regression problem. I do have the situation that I have some data points. And in that case, both my horizontal and my vertical axis are inputs. And basically the color of my data points tell me my output. It tells me it belongs to class 1, the blue ones, or it belongs to class 2, the red ones. And I do know for all of my data points, I do know which class they belong to. They are pre-labeled. Inputs can again be any kind of information from the process. And overall, I want to have something like a separation line between those two classes that tells me, oh, if I'm on this side of the line, this is my class 2. If I'm on the other side of the line, this is my class 1. And of course, I can extend that framework to more than just 2 classes and to higher dimensions than shown here. I'm going to introduce three different classification algorithms to explain the corners of the triangle that I'm going to show you later. So we'll have the same framework as before. But just to give you a bit more context about those corners, I'm going to introduce 3 algorithms, one from each corner. The first one is called Fischer discriminant analysis. And basically what is happening is that this is an algorithm that tries to maximize the scatter between 2 classes, which is shown here as the SB. So it's basically the distance between the 2 classes. And then it tries to minimize the scatter within each of the classes, which is S1 and S2 here. And that is pretty intuitive if you think about it. I want my classes to be as close, like I want all the samples in my classes to be as close to the other samples as possible and as far away from other classes as possible as well. That is shown here in this objective function. SB is the scatter between classes. I want to maximize this. SW is the scatter within classes. I want to minimize that. And if I go through the math, I can come up with this discriminant function. And then if I basically say that my delta of my 1 class is equal to the delta of my 2nd class, I can come up with this separation line. So overall, this gives me an idea of how I can come up with a separation line, as I mentioned it before. In that case, it's shown here. One of the important things for this algorithm is that it considers the data to be normally distributed. if they are not normally distributed, it doesn't perform as well. It's not a good choice to choose this algorithm. So you can probably guess from that that normality is one of the corners in the triangle. And this is the next algorithm. I've already talked about random forest before, and random forests can be used with classification trees or with regression trees. If I use regression trees, I get a regression problem, and then classification trees do the classification as shown here. It's a pretty straightforward framework. Basically, I can define separation lines on my plane based on my inputs. So let's say my x1 is my horizontal axis, my x2 is my vertical axis. And then I say, oh, is my x1 greater than 4 or less than or equal than 4? If it is less than or equal, I already know all the values that are on the left-hand side of this separation line belong to class 2. And then if I say it is actually greater than 4, then I'm on the right-hand side of the separation line here. And then I actually do not know, do they all belong to class 1 or do they all belong to class 2? Because some of the class 2 data points here on the right-hand of this line. So what happens afterwards is that I actually look into other variables. And then I can look at the x2 variable and I can say, oh, if it's greater than 5, then I'm in class 1. And if it's less than 5, I'm in class 2. So I do have this kind of hierarchical structure where I would split it on my variables, and then there are refined algorithms that do that for you if you apply one of those algorithms. So in general, one of the things you can see is that this separation line here is not linear. Because how would you define a linear classification problem is if your separation line is linear. So if you just have one straight line. If you have something like that, where you have several lines, or you have like a bent line or something like that, that is considered nonlinear. So one of the so random forest is, for example, is an example for a nonlinear classification algorithm. And similar to before, we also have dynamics that can be considered. And in that case, there's something called dynamic time warping, which in a simple approach, if you have two different time series, you can just use Euclidean matching. So which means you would map point 1 in time series 1 to point 1 in time series 2, point 2 in time series 1 to point 2 in time series 2. But if you use dynamic time warping, you actually allow for certain shifts. So the first point in this blue time series might be mapped to the 5th point in the red time series. And with that, you can actually identify certain dynamic patterns. And you can either use it in like algorithms that, for example, nearest neighbor dynamic time warping. Nearest neighbor is a typical nonlinear algorithm where you just look at points around the point you want to classify in your training set. And then you just look, okay, I look at the 5 closest ones. If 3 or more are in that class, I assign it to that class. So you can combine that. But usually if you use nearest neighbors, you use the Euclidean matching. But in that case, you would just use the dynamic time warping matching to do that. Alternatively, you could use dynamic time warping to just extract a certain type, to extract new types of features based on your prior features that do consider the dynamic effects in the data. So this is generally one way to handle dynamics. And then based on those 3 algorithms, you come up with this, or like those 3 algorithms are an example of 3 corners in this triangle, where I have normality, FDA, Fischer discriminant analysis. Nonlinearity has random forest here, but also k-nearest neighbors and kernel support vector machine. And then dynamics has the dynamic time warping feature extraction. And then on the edges, we have again algorithms that combine that. And in the center, we have algorithms that are suitable for all of those. Okay, any questions? All right, then I would just continue with how do we determine those characteristics. You can see that 2 of the 3 characteristics are actually the same as in regression. And for dynamics, we can actually use basically the same approach. We're also using the autocorrelation. So that is a very simple one with like some minor differences that I already talked about. But then nonlinearity, although it's the same characteristic, it is very different in the way it is determined. And normality, we need to come up with something as well. So that is shown here. Normality is generally a pretty well, or detecting normality is a pretty well-defined problem. There are lots of different algorithms. So I basically just did a literature search and found this Roy's test, which is based on the Shapiro-Wilk test, is known to perform pretty well for multivariate normality detection. So I've just implemented that. That seems to be working pretty well so far. So that is pretty straightforward. And then dynamics. Here, we already talked about that. So basically, it's the same idea. It's the exact same slide. But in that case, I just analyzed the inputs. And that is still kind of something that I'm working on, because you cannot apply autocorrelation on the outputs. But I do believe that the outputs are the better indicator. Yeah, so if you have any ideas for that, I'd be very interested in hearing them. At the moment, I'm just analyzing the inputs, and I'm looking at how many of those inputs do actually have dynamic correlations. Alternative models would be something to do, also a two-step model where I first analyze nonlinearity, normality, apply my algorithm, see if there are any weights assigned to the different features. In that case, I could just look at my weights and look at which of the high weight ones do have dynamic correlations. But that is not the case for all of the algorithms. So yeah, those are just some thoughts that I had. At the moment, it's just looking at the inputs. And then the last characteristic is nonlinearity. And that is quite a bit harder than the regression case, because nonlinearity is defined in a very different way. In regression case, I basically have is y is not a function of x plus a constant, but it's a function with some nonlinear transformation of my inputs x. Then I know I have nonlinear effects. For classification, it is defined very differently, and you can see that on the right-hand side in the picture. So we have two different separation lines here, the dotted one and then the solid one. And for the dotted one, this is considered a linear decision boundary because it is just a straight line. And then the solid one is considered nonlinear because it bends and it's just not straight. So in that case, if I have this data set, actually the nonlinear decision boundary gives me a perfect separation. But the linear decision boundary might actually be a bit more general, because I don't know whether this point x3 is maybe just a bit of an outlier or like y2 in that case. So it is a question also, to which extent do I have nonlinearity in my data set? And yeah, in order to determine the nonlinearity in the data set, I used a fairly simple or intuitive algorithm. In the first step, you would choose one random sample from any of your training data points. In that case, let's say we choose x1. In the second step, oh, sorry, the first step is actually applying nonlinear classifier as shown by the solid line. Forgot to mention that. So I do have this nonlinear classifier predefined. Then I choose my sample, in that case, x1. And then the step after that is that I would choose a sample from the same class. In that case, let's say I chose x2. And then I would choose randomly any point in between x1 and x2. So at any point along this green arrow here. And what can happen here is that if I choose a point roughly in the middle, it's approximately where y2 is here, then I actually have a situation that the point in between 2 points from the same data class would be classified as a point from a different data class if I apply this solid line. So what is happening is that I just perform this again and again, and I count how many times do I have a point in between 2 points from the same class that would be classified to a different class. And this is kind of a label switch. So I would count the number of label switch over the number of times that I've repeated this experiment. And if I actually have like a linear decision boundary as in the dotted line, this is absolutely impossible. Because if it's just like a straight line, you cannot have any 2 points from one side of the line that would have a point in between them that is part of the other side of the line. So the more nonlinear my decision boundary is, so the more like those curves and goes back and forth, the higher this value will get. So this is why I thought of it as a measure for nonlinearity, or actually this is This is from this paper, and I implemented it as my nonlinearity measure. There's still edge cases you need to consider. So this all works very well, but in this case, I do have two normally distributed classes that are centered at something like -3,0 and 3,0. So like one center is approximately here, the other center is approximately here, but their variance is fairly big, so they have overlap. So if I now apply my one nearest neighbor, my nonlinear decision boundary, that is shown on the right-hand side here, and it just shows you which areas would be classified to belong to the red and which areas would be classified to belong to the blue. And if I choose now, let's say the point where my mouse is here in blue, and then this other point also in blue, I can have a situation where in between I end up in the red. So I would have a nonlinearity measure that is actually higher than 0. But if I think about it, if I have two normally distributed classes that are the same, just shifted, the perfect separation line would be actually in the middle of those. So if I have 3,0 and -3,0, at the 0 horizontal line would be the perfect separation in that case. So by introducing this additional measure, I want to avoid those overlap cases where I actually do want to have a linear separation boundary, but my overlap causes it to have nonlinear, or causes my prior algorithm to detect nonlinearity in the data if I just follow it. So I came up with another overlap measure, which is also pretty simple. I would first apply a one nearest neighbor, and then I just choose a random data point, and I just count how many times does the closest data point to this belong to a different class. If I have no overlap, the classes are perfectly separated. I do not expect this to happen very often, or basically not at all, because the closest data point should always be a data point from the same class if they are perfectly separated. So this gives me an idea of how much overlap is in the data. And then I just combine those two measurements by saying, okay, my nonlinearity measure increases if there's nonlinearity. In my overlap measure, this also increases my nonlinearity measure without there being any nonlinearity present in the data. So I look at the ratio, and then just like by trial runs with different nonlinear and linear data sets in different shapes, I've played around with that. I've come up with this value of 0.2. So if it's greater than that, I would define it to be nonlinear. If it's smaller than that, I would define it to be linear. Okay, so that was the algorithm, and the next step would be the case study. So if you have any questions at this point, let me know. Okay, then I'm just going to continue. So this is another case study that we've been working on. So this is a fermentation process of Picapostorious cells, and those cells actually create a non-replicating rotavirus vaccine. So the goal of this whole process is to create as much of this rotavirus subunit vaccine as possible. It's operated at given conditions, and the situation is that first I have glycerol in my reactor, and then I just have like I start the reaction and my cells start growing. And then after a while, I add more glycerol into it. And then after a certain amount, I have reached my threshold in cell density, or like I have enough biomass in my reactor. And then I would add methanol. And methanol itself is what causes the production of this non-replicating rotavirus subunit. And that is why I looked into basically something like a fault detection, where I compared different runs with different methanol feed rates. So we do have those runs that are basically identical besides the methanol feed rate. And that is an interesting problem, because if you have your reactor running and you actually have a change in your methanol feed rate, you want to know about it, because that significantly influences the amount of your product, of your subunit vaccine. So I've tried to formulate that as a classification problem, and I do have those different measured variables. I have the O2 content, the CO2 content, that's just what's coming out of the reactor measured. And I do have the amounts of protein, ammonium, potassium, and phosphate in my reactor. And what is happening is that I have online measurements for the off-gas contents, which is measured every 12 seconds. But then the concentrations of the different components are measured offline, so manual, which means I do have them much less frequently than every 12 seconds. So in order to formulate a reasonable problem, I had to interpolate my concentrations for every 12 seconds. So I would have enough measurements. This is something you need to be aware of, because in that case, I have the situation that I actually have a direct dependence on my prior values for my concentrations. Because if I just do a linear interpolation, I basically have my 2 points, and all the points in between depend on those 2 points, and they depend on the point before and the point afterwards. So I will expect my algorithm to detect dynamics in the data. But even if it detects those, I can actually not be sure whether there is dynamics or not, because I've manually introduced them. So that is something to know if you look at the results. And then
Yeah, Fabian, I don't want to cut you off, but I also don't want to keep people too much after 6:30. So do you have a summary slide for this section you might be able to show us as we wrap up?
So those are already the results.
Oh, okay, perfect.
So those are the case study results. So what is happening, I have like nonlinearity was detected in all of them. And it makes sense that those are all the same characteristics, because it's basically the same runs. I've just combined them differently to also see that it doesn't even matter what is your training, what is your testing too much. And then dynamics is in brackets because I cannot be sure whether it's really there. So what is happening in the triangle? I looked at nonlinear methods and then nonlinear dynamic methods. And then I just applied them. And what is happening is that in like most of the cases, it actually is the best performing algorithm. And then in 2 cases, it's still performing reasonably well. It's the second best performing algorithm. So overall, like those are pretty good results. And you just apply the algorithm. You don't need to know a lot about the data. You don't need to know a lot about the methods. Yeah, it's just like, it's a pretty convenient way to deal with data. Yeah, and yeah, acknowledgements, the FDA, and yeah, that's kind of my presentation. I think, yeah, it's 6:30, so if you have any questions, feel free, but yeah.